let's evaluate some definite integrals using the limit definition. So I've got the integral from 3 to 8 of 6 dx, and I have the integral from negative 3 to 4 of x dx. But I'm going to start over here because for some reason constant functions are actually usually harder for students to understand, so I'm going to start over here. So what we're going to do is we're going to look at this function, okay, x. Well, x is a polynomial function, and polynomial functions are continuous everywhere. So since this function is continuous from negative 3 to 4, we know that it's guaranteed to be integrable. Since it's guaranteed to be integrable, we can set up a regular partition. Remember, that means that it's evenly spaced. That means that delta xk is b minus a over n. And in this case, a is negative 3, b is 4. And since it's guaranteed to be integrable, we have to pick some ck in those subintervals. Now this is going to be a little tricky, but in the case of regular spacing, this is how it always works. It's a plus k delta xk. So why is that true? Well, let's think about this. So this is really what it works out to be. When I have the first c value, so let's say it's like the c0 or c1. Well, if it was c0, let's just say it's the c0. Then k is 0, and that means we started at a. And that will be in the case that we take the left endpoint. That would be the case we take the left endpoint. But if we don't, then let's say we're taking all the right endpoints, then k goes 1, 2, 3, blah, 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 all the way to the nth value. So then in c sub n, k is equal to n. These cancel. B minus a plus a is b. So what you're really doing is you're saying, I'm just taking the kth chunk of that. So I start at a, and then I walk 1 chunk and 2 chunks and 3 chunks, 4 chunks, 5 chunks. And those are my evenly spaced points. So this is the general format. So you have negative 3 plus 7k over n. So then when we do that, we're going to, this is our piece. That's our delta xk. So we do the limit. In this case, we can do the limit as n goes to infinity. We don't have to do the norm of delta because we're using regular spacing, so it's just directly tied to n. It's not tied to the width. So that integral, well, I could call it a, but let's call it negative 3 to 4 x dx is from k equals 1 to n of, well, f of ck delta xk. Now, f of x is just x, so it is just ck, right? So that gives us just whatever ck was, which is this, negative 3 plus 7k over n times delta xk, which is 7 over n. If we multiply this out, we get negative 21 over n plus 49k over n. But these n's and 21s and 49s are actually, those are Those are all constants relative to the sum. So we can pull out the 49 over n, and we can pull out the negative 21 over n. This just becomes n, and then this over here becomes made a mistake. Okay, so this is good. This is good. It's always good to catch your mistakes. So this is negative 20 over n, but this is n squared. Because otherwise that would have been problematic. You would have had something not go through. So these become n squareds. So we'll have these n's cancel. You have negative 21 plus 49 n plus 1 over 2n. So that's a little bit odd. Now you could do a decent amount of simplification. You could do 49n over 2n, and so that would give you negative 1 plus 49 over 2, and then you'd have plus 49 over 2n. And that's a perfectly good way to do that. Another way to realize is that as n and n plus 1 go to infinity, both of those converge to the same value. So you could do this polynomial style, and since you have 49 over 2, you're going to get the same thing happening here. As n goes to infinity, that drives down to 0. So you have negative 21 plus 49 over 2, which is, what, 24 and a half. So you end up with 7 halves. So let me kind of evaluate that. And that seems to be correct. This should be 7 halves. Let me check my cheat sheet. Alright, cheat sheet's correct. Alright, I did it right. So let's do the same idea, but instead let's do it with 6 over here. Now, this one's actually going to be even easier, because in this particular case, a is 3, b is 8, and f of x is 6. So no matter what, we actually don't have to worry about this case over here, because this is not going to change. But we'll go ahead and pick our ck anyway. So our delta xk is b minus a over n, which becomes 5 over n. And then our ck is a plus k delta x k, which is 3 plus 5k over n, right? That's our ck. But again, we're not going to be using that, but it's just there for us. So we take the limit as n goes to infinity. We don't have to do the norm of delta. Or rather, k equals 1 to n of f of ck delta xk. But f of anything is always 6 is a constant function. So this is just always going to be 6. And then this is going to be 5 over n. So we can pull that 30 over n out, because 30 over n, we'll just pull it out here. And so this is just 1. But we know that the sigma sum of 1 from 1 to n is just n itself. And that the limit of a constant is a constant. 30. Now, this is probably very... You could have seen this without having to do this, because if we were thinking about this like an area, if I have something that is a height of 6 over a width of 5, because I'm going from 3 to 8, so so width of 5, a height of 6, that's a rectangle with area 30. But hey, this is a good way to kind of verify that without, verify something you kind of already know, but get used to a technique before you go on to do something you don't know that well.